All right, what do you guys want to talk about?
I have a question about one topic.
Sure.
With the last section with the transient, how do you know if you're supposed to use the equation that analyzes infinity or not? Will you just ask for it?
So for the exam, yes, but generally speaking, you would analyze the circuit at t is equal to infinity if there are any independent sources that are still connected, and I don't mean directly connected, but still connected to your energy storage element. So for example, if we had a circuit like this, I'm just going to do this generically, so I'm not going to worry about numbers or anything. Call this R1, R2, L. Particular circuit, it doesn't really matter if the switch is opening or closing, that voltage source Vs is still connected to the inductor. So this would be an example of a total response problem, okay? But if we had, so I'm just going to arbitrarily say closing at t is equal to 0, it could just as easily be opening. But for a circuit like this, opening that switch completely disconnects IS from being able to influence the behavior of C at all. So the second one would be an example of a natural response problem where you wouldn't need to analyze a circuit at infinity. Now, generally speaking, there's literally nothing wrong with you treating every problem as if it were a total response problem. The only thing that you're going to wind up doing is wasting a little bit of time proving that the signals go to 0 at t is equal to infinity. All right, what's next? Michael. So inductance, oh gosh, let's see. There are a couple of different ways to describe inductance. Inductance is the change in magnetic flux caused by a change in current, or is it the ratio of the change of magnetic flux caused by a change in current? It could be defined as how a circuit or element reacts in the presence of a changing magnetic field. It'd be defined as the property of a element to oppose a change in current or a change in magnetic flux, since those two things are linearly related. I think those are all the different ways that you can reasonably describe it.
voltage or the
No. Other than the fact that your voltage drop across an inductor equation, V is equal to L di by dt is literally Faraday's law of induction. But other than that, no. Yes, sir. Number 20 on winter 2019. This one right here, right? All right, so we are given the current flowing through our capacitor, and we are asked to find the voltage drop at a particular time. So that relationship is V of C is equal to 1 over C times the integral from T naught, some point at which the capacitor voltage is known, to some later point in time T of IC prime T prime plus VC at T naught. Now, I'm not actually expecting you to use this relationship, but it's kind of telling us what to do, okay? So it's going to be the area under the curve from time when we know what the capacitor voltage is, so 0, to the time that we want, which is 4 milliseconds. So effectively, that means we need the area of this triangle minus the area of this triangle. And then, actually, let me do it. Plus the area of this rectangle, plus the area of that triangle, all added together. We divide it by C, and then we add 6 volts to it. That, pardon? Yeah. Oh yeah, that's really hard to do. Yeah, don't do that. Yeah, if I give you a graph, I would say there's a more than a 99% chance I'm just expecting you to either add up the areas of triangles and rectangles and such, or effectively take a derivative, which is just find the slope of a line. Yeah, if you're trying to do real calculus, anytime I give you a graph, you're probably doing it wrong. What's next? Sure. Okay, so just very, very generally. So a 5-minute crash course in transient analysis. The first step is to analyze the circuit at T is equal to 0 minus. Since T is equal to 0 minus represents a DC steady state condition, that means we will replace inductors with short circuits and replace capacitors with open circuits. And I'm going to just throw this out here as well, even though you may not explicitly be asked to do this in the problem. I'm going to tell you, regardless of whether or not you are asked to do it, you need to find the inductor current at t is equal to 0 minus, or if it's a capacitor problem, you need to find the capacitor voltage at 0 minus. Step 2. I don't know why this thing won't go away. There we go. We're going to get to that in a moment, but you're 100% right. Yes, neither of those quantities will change between 0 minus and 0 plus. So step 2, to analyze the circuit at t is equal to 0 plus. And here, we will replace inductors with current sources having the same magnitude and direction as IL at 0 minus. And we will replace capacitors with voltage sources having the same magnitude and polarity. As VC at 0 minus. And then after we do that, we would obviously solve for whatever quantity we were interested in. Step 3, and I'm going to put a star by this because we only have to do step 3 when there is a independent source connected to the energy storage element of interest at t is equal to infinity. We're going to analyze the circuit at t is equal to infinity. Give me just a second and I will explain it. All right, so if I scroll up here, the top circuit is an example of when you would have to analyze it at infinity because the voltage source is still connected in some way, shape, or form to the inductor L at t is equal to infinity. So a long time after the switch is closed, the voltage source is still influencing the behavior of the inductor. For the bottom circuit, a long time after the current source is, or excuse me, after the switch is opened, the current source is incapable of influencing the behavior of the capacitor. So effectively, if you disconnect your independent sources from your energy storage element, you don't need to analyze that infinity. If there is any independent source still connected after the switch changes state, you do have to analyze that infinity. So it will become 0 only when you're disconnecting things. Yes. So for the case where it's still connected, effectively what you're doing is you're applying what's called a forcing function that is going to force your energy storage element to have some non-zero value at t is equal to infinity. Anytime that's the case, you need to analyze the circuit at t is equal to infinity. Anytime you don't have a forcing function connected to your energy storage element, you don't need to analyze it at infinity. All right, so analyzing the circuit at t is equal to infinity. At t is infinity, since this is a long time after the switch has changed state, we are again at a DC steady state condition. So that means that we will replace our inductors with short circuits, and we will replace our capacitors open circuits. Okay. And then we will just solve for our quantities of interest at t is equal to infinity. Step 4. Is to determine our time constant. Tau, where tau is equal to L over R for RL circuits, and tau is equal to R times C for RC circuits. And R is the Thevenin equivalent resistance seen by L or C. I'm saying that very explicitly, the Thevenin equivalent resistance, to remind you that you are supposed to turn off your independent sources, because anytime you're calculating the Thevenin equivalent resistance, you do so utilizing a dead network. Step 5 is just apply the generic equation. Y of t is equal to y of 0 minus, or t less than 0 minus. It is y of 0 plus minus y at infinity e to the minus t over tau plus y at infinity t greater than or equal 0 plus. Yes, sir.
What is that before or after?
So it's during the transient condition, because it has to be when the things are in a state of flux. The circuit doesn't really have a time constant for t less than 0 minus or for t greater than infinity, because nothing is changing, and tau effectively represents the rate of change for the system. So it's during the transient condition explicitly. That's correct, because you're turning them off. So you want a 0 volt voltage source, which is the same as a short circuit, or a 0 amp current source, which is the same as an open circuit. What's next? Number 24 on winter 2019. Okay, so this is a capacitor combination problem. So the first thing that I'm going to do is identify nodes. So this is node A. I'm going to call this guy C. Let's call this guy D. This is B. This will be E. And finally, this guy over here will be F. I'm trying to find the equivalent capacitance seen between A and B. So I'm going to put A over here on one side and B over here on the other side. So to go from A to B, it seems fairly obvious that I have to first go to C, as that's the only route I can take to leave node A. So I'm going to put C here. From A to C is the 14 microfarad capacitor. Like so. And I'm going to check mark there. Okay. Now, to go from C to B, the shortest path is to go from C to E to B. So I'm going to put E here. And to go from C to E, I can go directly through my 66 microfarad capacitor. I can go from C to D to E. So I'm going to put D here. From C to D, I have two paths, the 16 and the 46. I can go from D to E directly through the 61. I think I said that was 61. I might need to double check that. Yeah, that's at 61. I've taken care of this 46. I've taken care of this 16. I could also go from D to F to get to E. So let's put F right here. And to go from D to F, I have two possible paths. So they are the 17 and the 94. From F to E is the 95. And and the only way I can get from E to B is through the 54. And at this point, I'd simply start doing the combinations, right? So the 16 and the 46 in parallel is going to look like 62. The 17 and the 94 in parallel is going to look like 111. And then I have some series combinations and all that kind of good stuff to do. But from here, it should be fairly straightforward. You just need to remember that capacitors in parallel combine like resistors in series. Capacitors in series combine like resistors in parallel. Is that sufficient, Kevin? All right. Michael. Close this thing. Fall 2020, exam 2. What problem with that again, number 20? All right. So we want the inductor current at T is equal to 8.4 milliseconds. And we are given IS of 0 and VS. Okay, so this is extraordinarily similar to homework 12, problem 5. So the steps that we would use for this problem in particular are that we would apply Kirchhoff's current law at this node. So that would tell us that IS of T is equal to IC of T plus IL of T. We know that IC of T is C dVs by dt, since the voltage source Vs is in parallel with the capacitor. That Vs represents Vc. So that's effectively how we would do number 19. And IL of T would be 1 over L integral from 0 to T Vs of T prime dt prime plus IL of 0. Well, this part right here is just calculus that you can throw in your calculator, right? This part right here is the less obvious bit, okay? So circling back to around to our original relationship that I wrote, my KCL equation, IS of 0 is equal to IC of 0 plus IL of 0. Because Kirchhoff's current law has to be true for all points in time and generally for any point in time, okay? Well, IS of 0 is given to you in the problem statement. IC of 0 is literally just this evaluated at T is equal to 0. And then from those two numbers, you can solve for IL of 0, which you would then substitute into your inductor current equation, and then you're done. So it is literally pretty much exactly homework 12, problem 5, which I warned you guys that I like and would put something similar to that on your exam. And then what do you know? Here it is. All right, so this is very similar to a homework problem as well. I think it's homework 12, problem 2 or 3. So effectively, this is almost the exact same problem, except you're doing a Kirchhoff's voltage law relationship as opposed to Kirchhoff's current law. And so what I mean by that, let's see. We're looking for VC, and that's the only thing? Okay. So if I were to write a KVL equation here, I would have Vs of t is equal to, let's just call it R times Is of t plus my capacitor voltage, which is going to be 1 over C integral from 0 to t Is of t prime t prime plus VC at 0 plus L dis by dt. So we are specifically interested. Another thing that I can write here, actually, let's do this. Vs of 0 is going to be equal to R times Is of 0 plus VC of 0 plus L dis by dt evaluated at t is equal to 0. And I need that to figure out what, shit, hold on. I need that equation at t is equal to 0 to figure out how the capacitor voltage behaves at 0. And then this guy right here tells me how the capacitor voltage behaves as a function of time. So extraordinarily similar to the previous problem that was asked about, except instead of using a KCL relationship, you're using a KVL relationship because all of the elements are connected in series. So KVL, if we have a single loop circuit, KVL is usually the analysis method to use. Even with these guys, if we have a single node pair circuit where everything is connected in parallel, KCL is going to be highly involved in the circuit's analysis. So that, okay.
And the thing you're saying about earlier where you underline the integral and the C at 0, it'd be as if you're taking an integral from 0 to 0, so it'd be times 0. So that's why when you're seeing something
Oh, actually, I didn't even realize that I was just asking you to do it at t is equal to 0. So you probably don't even need that top equation. I wasn't even paying enough attention. You could literally just use the second equation there and get everything that you needed. I thought you were asked to find the capacitor voltage at some other time. So yeah, so that means that it's literally just this equation right here, and then you're solving for that VC of 0 term. And then you're done. Yeah. Alrighty, so this is a Thevenin and Norton equivalent circuit problem. We're asked to find the Thevenin resistance seen between terminals A and B. And this circuit contains only a dependent source, right? There are no independent sources, which means the only way in which we can analyze this circuit is to apply the test source method, okay? So for the test source method, we choose whether or not we want to apply a voltage test source or current test source across the terminals of our network. In this case, I am going to explicitly choose to find, or excuse me, choose to use a voltage test source. And I'm going to call it a 1 volt source. Now, the reason why I'm using a voltage test source in this particular problem is because I have just decided what the voltage Vx is, right? My goal here is to figure out what this current I test is, because I know that R Thevenin is equal to V test over I test. Well, I can figure out I test by simply applying Kirchhoff's current law. So I test, in this case, is going to be 1 volt over 16 ohms plus 6 times Vx. So that's 6 times 1. And then I plug that into my equation and I'm done. What's next? Yes, sir. All right, so the Thevenin voltage, positive polarity reference on the top left. Okay. So effectively, I'm trying to find this voltage. So I'm going to do that using, let's see, I have 1, 2, 3, 4 nodes, one of which will be ground, or I have 3 meshes. So it's going to be a 3 equation, 3 unknown system either way. Because I'm trying to solve for a voltage, I'm going to use nodal analysis. So the question then becomes, where do we put our ground? I'm going to put ground here, literally just so V Thevenin and VA are the same thing, okay? I'm going to call this node then Vx, this node Vy. So I have, that is not what I meant to do, okay. I have a, all right, so going through the nodal analysis steps, we've identified our nodes, we've labeled, we've selected our reference, we've labeled our nodal voltages. We don't have any dependent sources, so we don't need to do a relationship for controlling variables. We do have a voltage source, so we're going to have a voltage relationship equation. So I'm going to say that 8.4 volts is equal to VA minus VY, because it's the nodal voltage associated with the positive polarity terminal of the voltage source minus the nodal voltage associated with the negative polarity terminal of the voltage source. I do have a super node that does not contain my reference. So I'm going to be adding up the following currents. This guy and this guy, and setting them equal to 0. Now, some of you may be thinking, oh, well, there's current flowing through the 11 ohm resistor that you need to take account of as well. If we include the 11 ohm resistor, we're going to have, in our supernode equation, we're going to have this current flowing down through the 11 ohm resistor, and this current flowing up through the 11 ohm resistor, and they're going to cancel each other out. So anytime I have a resistor directly in parallel with my voltage source, it doesn't need to be in my supernode equation because the currents cancel each other out. So just skipping that bit right there. This is going to look like 2.1 amps plus Vy over 7 ohms is equal to 0. My third equation is going to come from applying KCL at node X. So I'm going to have negative 2.1 amps plus Vx over 8 plus Vx over 5 is equal to 0. And I'm done. Right, 3 equations, 3 unknowns, solve for VA. Once I have that, I'm finished. Yes, so if I'm applying KCL at a supernode, right, I have to find all of the currents leaving both terminals of that supernode, okay? So that would be the current leaving node A through the 2.1 amp source, the current leaving node A flowing down through the 11 ohm resistor, the current leaving node Y through the 7 ohm resistor, and the current leaving node Y flowing up through the 11 ohm resistor. Well, I have the current flowing down through the 11 ohm resistor plus the current flowing up through the 11 ohm resistor. Those two have to represent the same current flowing in opposite directions. So when I add them together, they just make 0. So I just don't put it in the equation because it's a waste of space. Yeah. So because it was a supernode, that's why I didn't need to include it. If I had chosen ground somewhere else, I likely would have needed to, well, I might have needed to include it. Let's just put it that way, just depending on things. But because of this particular analysis method, I did not need to. You can. That will absolutely work as well, yes.
Would the Norton current, would that short out anything, or does the current still stop that?
The Norton current. So if I were to short terminals A and B, that short is not directly in parallel with any of the elements in our circuit. So I would argue that it doesn't short out any particular elements. And now it might short out combinations of things, but that's kind of hard to see those effects and quantify them easily. So because the short circuit isn't directly in parallel with anything, I would definitely go with a full circuit analysis approach just to cover my ass and make sure I didn't make a mistake. Yes, sir.
So for number 7, could you just take the Thevenin resistance to find that Norton current? Would that be the same?
Yes, and honestly, I believe that's what I would more likely do than calculating the Norton current directly, because, or at least calculating the Norton current using mesh analysis is going to be difficult because there are 4 meshes as soon as we short that guy out. So our options then would be to apply nodal analysis and then use the results of that nodal analysis to determine the Norton current. Or we can simply take our answer from number 6, divide it by the Thevenin equivalent resistance, which is pretty easy for a circuit like this, and then get the same result. So I personally wouldn't actually calculate the Norton current here.
And then how do you know that VA is the one that's going to equal the VTH?
Okay, so the positive polarity terminal of V Thevenin is associated with node A. The negative polarity terminal of V Thevenin is associated with node B, which I have selected to be my ground. So the positive nodal voltage VA minus the negative nodal voltage 0 is equal to V Thevenin. So VA is V Thevenin.
So on the last problem, that was the test source method.
Right.
The only the test source method running there is just the dependent source.
Yes, you can use the test source method anytime you're trying to calculate the Thevenin equivalent resistance directly. But if there aren't dependent sources, I would argue that resistor combination techniques are much easier to calculate the Thevenin equivalent resistance with than using a test source method. So in practice, we will only use it whenever there is only dependent sources in our circuit.
When we're doing transient analysis, that technically, whenever we replace the capacitor.
No. So what we're doing when we replace the capacitor with a voltage source and an inductor with a current source at T is equal to 0 plus very explicitly, is we are exploiting the fact that since capacitor voltage cannot change abruptly and inductor current cannot change abruptly, our capacitor is going to have a very specific fixed voltage at T is equal to 0 plus, which is entirely independent of the amount of current. So at that specific instant in time, the capacitor is behaving like an independent voltage source. And similarly, the inductor is behaving like an independent current source. Right, because that graph is common for everything effectively. They all behave like that, so it's kind of irrelevant. It's all going to be some sort of exponential decay. Yes.
So for problem 8 and 9 on this test, would you use the test method and then test I test is equal to 1 since the dependent
All right, so 8 and 9 here, I would not use the test source method at all. Okay, there is an independent source, which means I can calculate V Thevenin and I Norton. And then I would use those two values, the ratio of V Thevenin to I Norton, to get the Thevenin equivalent resistance. You could, if you were so inclined, determine one of those two quantities, V Thevenin or I Norton, using whatever circuit analysis technique that floats your boat. And then you could turn off the 17-volt source, use the test source method to find the Thevenin equivalent resistance, and then use that Thevenin equivalent resistance as well as the other quantity that you calculated to determine the third unknown. But personally here, looking at this particular circuit, I would just find V Thevenin directly and I Norton directly. Because for V Thevenin, it's just the voltage drop over the 9 ohm resistor. And you effectively have a single loop circuit there because no current can branch off and flow through the 10 ohm resistor. And for I Norton, that's just a 2-mesh circuit to analyze. So I would argue that that's the easier method to use. So that's one of the biggest problems with circuits is that there's so many things you can do. It's a question of what thing you should do to make it the easiest possible problem to solve. All right, what's next? Sure. Attach my keyboard real quick. Figure out, there's my cursor. Which problem am I looking at? I don't like this problem purely because, in my opinion, it doesn't teach you anything new about transient analysis whatsoever. This is more so an exercise in applying nodal analysis or mesh analysis more so than transient analysis. So the steps that we detailed previously regarding how you would apply transient analysis would absolutely be applicable here. But if I'm just looking at this thing, I see, so during the transient condition, there would be 1, 2, 3, 4, 5, 6, 7 meshes to analyze. And I don't know, there's a whole shitload of nodes. So if you'd like to talk about this particular problem later in the day, I'd be happy to help you through it. But I think it would be a waste of time setting up 7 equations for right now when I guarantee you there's nothing this ludicrous on your exam. Does that sound reasonable? Yeah. Colby.
Number 11 on the fall 2020 exam. So for that one, you have the capacitor in there with it. What do you do?
Okay, so for this particular problem, recognize that all of your sources are DC sources, which means that your capacitor is an open circuit and your inductor is a short circuit, right? So let me, excuse me. If we were to treat we'll need that value in a moment. But if we were to treat this as a short circuit carrying a DC current IL, and we were to treat this as an open circuit over which a DC voltage VC appears. To solve problems 11 and 12, all we need are to know that current IL and that voltage VC. So how could we go about solving for those two quantities? Anybody have any thoughts? KCL, okay. So this node right here. That can be of use. I would argue that a single application of KCL probably isn't going to give us all the information that we need. Nodal analysis or mesh analysis here would be right, but it's just multiple applications. So we'd be applying it effectively everywhere. Yeah. So the question is, which would be better here, mesh or nodal? So if we did mesh analysis, we already know. So let's draw this out real quick here. So we have this one loop, all that IA. This second one here, IB, and we can see by inspection that IB is -3 amps. So we only have one unknown quantity with which to determine, that would be IA. And in this case, IA and IL are the same thing, right? So if we did mesh analysis, we solve for IA, we have IL, and therefore problem 11 is taken care of. And then we could do Kirchhoff's voltage law around this path once we know IA in order to solve for VC. So that's definitely one way that we could go about doing it. We could also use nodal analysis, which is what I believe Connor was suggesting here. So let me erase some of this stuff. And let's talk about how we could do nodal analysis pretty quickly as well. So recognizing that if we put our ground node right here, then whatever node this is, that has a value of 24 volts. Whatever node this is has a value of 9 volts. We could lump these two together into a single 28 ohm resistor, meaning that this would be our only unknown voltage, nodal voltage, which would allow us to calculate VC easily. And then we could apply KCL at this node X to figure out what the current IL is very easily as well. So either nodal analysis or mesh analysis will get you both quantities of interest in like 2 steps. So it's really whichever one you feel more comfortable with. The nodal analysis method, though, will take slightly more steps if you do not combine the 21 and 7 ohm resistor that are in series there. But it's literally just adding a single node. So it's not like vastly messing things up.
So none of these practices have object on it,
So we have covered op amps prior to exam 2, but op amps are not material for exam 2. So much like we covered Thevenin and Norton equivalent circuits before we had exam 1, they didn't show up on exam 1. Yeah, so the material for exam 2 is Thevenin and Norton equivalent circuits, capacitors, inductors, and then transient analysis of RL and RC circuits, and that's it. All right, what's up? What's next? All right, so nobody's saying anything, so review session done. If I'm being entirely honest, I'm not 100% sure where your exam is tonight. We've had some issues with other exams being scheduled on the same nights as ours, and it has happened yet again. I believe that our exam is supposed to be in 105 and 108 for standard time students, and in here for extended time students. I emailed Ashley Osborne, who's been helping me coordinate all of this stuff yesterday, but she has not yet responded to my email to verify where the test is being held. So I'm gonna go down the hall and harass her. And I will send out an email over Moodle to everyone telling them, you know, like where they're supposed to be and all that kind of good stuff. So I will let you know, hopefully within the next 10 to 20 minutes, where the hell this exam is being held. Connor, do you have a moment?